pretty funny cartoon, I have to say. With everything that's going on with the COVID-19 infection rates, we have seen some excellent applications of exponential functions. So I think this is a great lead in to our work in Chapter 5. We'll be working with exponential functions and logarithmic functions. And so let's go ahead and get started. So let's check out exponential functions and their graphs. We're going to learn to evaluate some functions with base A. So we need to understand the difference between a base and an exponent. We'll graph some exponential functions. We'll use a one-to-one property. We'll do some evaluation, and we'll do use exponential functions to model and solve real-world problems. So, what is an exponential function? We've seen the good old quadratic function. Worked a lot with him, x squared. We've worked with polynomials, x cubed minus 3x squared. We've worked with rational functions. These guys are all algebraic functions. When we switch the base, in this case, which is x, and the exponent in that case, which is 2, when we switch those two out, where the 2 becomes the base and the x becomes the exponent, we have now transformed this into what we call a transcendental function. And a type of transcendental function is our exponential function. So now what we'll see is the exponent is going to be the variable and the base is going to be a constant. So we're going to have some number raised to an unknown power x. Whether it's 2 to the x or 3/4 to the x, we can see that the base of 2 and 3/4 is constant, and it's the exponent that now will vary. So that changes the game with respect to the shape of the function and its properties. So here's the definition of an exponential function. F of x equal a to the x, where a is our base, x is our exponent, or it can be written as y equal a to the x. Remember, we can replace f of x with the letter y. Now, there are some conditions on our exponential function, which is a, our base, has to be greater than 0. So we can only have a positive number base, and a can't be 1. Now, let's just investigate why we have to have those two restrictions. First off, what if the base was 1? And I started plugging in some values of x, like f of 1 and f of 2. What's going to happen when you raise, what's going to happen when you take 1 and raise it to a power? It's going to always be 1. So this case we don't consider when we're working with an exponential function. A cannot be 1. Why is this guy not an exponential function? Because it's quadratic. The base is your variable and the exponent is constant. That has to be switched for exponential functions. Why is this guy not an exponential function? Because the condition says a has to be greater than 0. And if you notice, your base, a, is a negative number. Can't have a negative base when we're working with exponential functions. And finally, why is this last one not an exponential function? That's because the base is not a constant. And the base has to be a constant. Okay, so now let's do some evaluation. So what you'll need to do is pull out your calculator and find the values of these particular expressions. So why don't you pause it? As I was saying before I was so rudely interrupted by that error message, why don't you pause the video, find the values, and then come back and see if your answers match. So now you can check your answers. First value, and we're going to 3 decimal places here. So the first value is 3.967 when I round it. Second value, 16.242, and last value, 0.016. And I've shown right below each one of those how you would enter that on your calculator using that caret key. And remember, that caret button is right below your clear button on the TI calculator. Okay, these values are calculated similarly. We're just going to plug in some values for x. So we want to find f of 0, so I'll plug in a 0 for x, 4 to the 0 minus 1. Plug in a 1 for x, 4 to the 1 minus 1, and so on. And then find those values. So 4 to the 0 minus 1 is a 4 to the negative 1 power. We have to remember our rules for exponents. When you have a negative exponent, you have to take the reciprocal. So 4 to the negative 1 is 1/4. And when I add that to 5 and work with the common denominator, I get 21/4. Plugging in a 1, I get 4 to the 1 minus 1, which is a 4 to the 0 power. And for my rules for exponents, what's anything to the 0 power? 1. So 1 plus 5 is 6. You can see how the rest of those were calculated. At any time, email me if you have any questions about anything that goes on in these videos. All right, so let's see. When we look at these guys graphically, let's see if I can bring that in just a little bit. Okay, so let's look at the graphs of an exponential function. Remember, it's y equal a to the x. And the base a has to be a number bigger than 1, and it can't be 1. So here's a case where a is bigger than 1. Let's say it's a 2 to the x, or a 7 to the x, or a 95 to the x. That base is a number bigger than 1. Here's what is always going to be true about an exponential function. Whatever the case, the domain will always be negative infinity to positive infinity. The range will be the same, again, regardless of the case, 0 to infinity. And these exponential functions, their basic shape will have a y-intercept at 0, 1. They will also both have a horizontal asymptote. Remember a horizontal asymptote? It's a line that your graph approaches left to right as x approaches infinity. So we're going to have a horizontal asymptote, and that asymptote is going to be at y equals 0. For both of them, they'll both, whatever the case is, increasing or decreasing, horizontal asymptote is at y equals 0. Also, these graphs are continuous. Notice this one on the left is an increasing function, hence exponential growth. And the graph over here on the right is the decreasing variety, which is exponential decay. The only difference in these two functions is that the base on the right-hand side, that base is going to be a number that is, excuse me, not the base. The exponent is going to be a negative. So over here I have an a to the positive x. That gives me my increasing function, exponential growth. Over here on the right, my exponent is negative, and that gives me a decreasing exponential function, which we call exponential decay. They all have the same domain, negative to positive infinity, same range, 0 to infinity, same y-intercept, just one is increasing, one is decreasing. And again, they both have that horizontal asymptote at 0. So these are the basic shapes we'll be working with in our exponential functions. This guy here and this guy here. So there's our basic shape. Those are our basic shapes. Now, if I take that basic shape and shift him up or down, I've got to shift the horizontal asymptote and the y-intercept up or down as well. So if I peeled off, let's say on the left, this exponential growth model, if I peeled off this graph and this dotted line and moved him up, shifted him up or shifted him down, the horizontal asymptote is going to go up or down, as well as the y-intercept. He will go up or down as well. So we'll have to shift both of those items when we shift up or down. If I shift left or right, notice the horizontal asymptote is going to stay at 0 when I shift left or right. So the horizontal asymptote doesn't change. So let's work on graphing some exponential functions. And we're just going to set up a table of values, and let's pick some values for x and find some values for y. So let me pick some values of x to be like -2, -1, and then 0, 1, and 2. Well, let's just plug those in. 2 to the -2 power. Well, negative means to take the reciprocal, so this will be 1 over 2 squared, which is 1/4. So when you plug in a -2, you get a 1/4. What about if you plug in a -1? Negative exponent, take the reciprocal, so 1 over 2 to the first power is 1/2. What if you plug in a 0? What's 2 to the 0 power? It's 1. That's your y-intercept. Doing the rest, 2 to the first power would be 2, 2 to the second power would be 4. We know we have a horizontal asymptote here at 0, so let's just plot those points to see that that exponential curve actually appears as we plot those points and connect them. So why don't you plot that and then fill out this table, and I'll pick some similar values, -2, -1, 0, 1, and 2. Fill out that table and graph that graph. So pause the video. So your graph with 2 to the x should be an exponential growth model. It's increasing. So we see that's the exponential growth model. And the one on the left, if we plot the points, finding the points, notice -2 comes up to be the number 9 because 1/3 to the -2 power, negative exponent means to take the reciprocal. Reciprocal of 1/3 is 3 over 1. And when I square it, change the negative exponent to positive, I get 9. So these are the ordered pairs for 1/3 to the x. When I plot those, I should see this exponential decay or this decreasing function. It looks like deer, doesn't it? Let's finish that word out. Okay, exponential decrease. So we can do these by hand. We can also put them in our calculator and get the same results. So remember our rules for transformation. I've got two functions and we want to describe the transformations here at the top. So I've got f of x, don't want that. I've got f of x equal 3 to the x, which is this graph here. Okay, f of x, or in this case, g of x is equal to 3 to the x plus 1. How does that graph differ from the parent function 3 to the x? Well, that plus 1 there that comes inside the function means we're going to go left 1 unit. And that's what happened. We shifted that guy left 1 unit. Horizontal asymptote stays the same. It's just that y-intercept ends up there. It's now at 3. Okay, let's recall if I have 3 to the x, what if I wanted to graph 3 to the x minus 2? And notice that that minus 2 is separate from the 3 to the x. That is a vertical shift. And remember, when you have a vertical shift, it goes in the direction of the sign of that number. So this guy is going to go down. If I can write that correctly, it's going to go down 2 units. Okay, so the horizontal asymptote for the original function was at 0, but when I shift it down 2 units, the horizontal asymptote is now at y equal -2. So when we shift up or down, we have to shift the horizontal asymptote up or down, and we're going to shift the y-intercept down. So the y-intercept now would be at -1. But we've done all this before back in chapter 2, shifting our functions up, down, left, or right. So let's check these last two transformations out. Parent function is 3 to the x. I would like to graph a -3 to the x. And remember, the negative in front just meant you flipped over or flipped across the x-axis. So it was a reflection across that x-axis. So our graph would look like the one you see here. That is a reflection across the x-axis. Last one to look at, the original function is 3 to the x. We see that parent function of 3 to the x. Now, what if I wanted to graph 3 to the -x? When the negative comes inside that function, and when I say inside, I mean in the exponent position, that's a reflection across the y-axis. We can always verify these by putting them in our calculator and graphing them. So if you happen to forget the rules, you can just graph it in your calculator to remember those. So let's do some graphing. Why don't you work on graphing these on your calculator? And then we're going to go ahead and state the domain, the range, and the horizontal asymptote. So take some time to do that and pause the video and then come back and check your work. So let's wrap up this first video from section 5.1 with these two graphs. If you go to your calculator and type in 2 to the x minus 3, you'll see this blue graph here represented below, and it's an increasing function. It's shifted down 3 units because we're subtracting 3, so the horizontal asymptote goes from 0 down to -3. The y-intercept goes down to -2. Now the domain is the same regardless of what we do to our exponential functions. It's always negative to positive infinity. But the range has changed because we shifted it down 3 units. So if you take a look at the graph, the range is going to be greater than the -3. So it's everything from -3 to infinity, but we cannot include -3. We have to have a parenthesis on it because there is an asymptote at -3, and we're not going to cross that asymptote. Big deal right there. The range is going to be based on your horizontal asymptote, and for the range, we cannot include that asymptote. And then the horizontal asymptote is at -3. We'll always see these two numbers with respect to each other in the range and the horizontal asymptote. If we go and graph this next one, -3 to the x plus 2, we're going to notice that it shifts up 2 units, and the negative in front of the 3 causes it to reflect across the x-axis. So when you put this in your calculator, you should see this blue curve. There's a horizontal asymptote at 2 because we shifted it up 2. So it went from 0 to 2. So y equal 2 is my horizontal asymptote. And domain is negative to positive infinity. You see there's an arrow on the left, negative to infinity, arrow out here on the right, positive infinity. The range in this case, notice the number 2 is involved in the range, but remember for the range, we always move bottom to the top. And since this graph is basically below that horizontal asymptote, the range is going to be negative infinity up to 2. But we can't include the 2 because he's an asymptote, so that's why we need a parenthesis. And the horizontal asymptote is at 2, so we write that as an equation, y equal 2. So look at the difference in the ranges here. As I move bottom to top on the first graph, I first encounter that graph here at the -3 mark, and then the graph continues to go up. So that's why the range starts at -3 and stops at infinity. Over here, the graph is below the horizontal asymptote, so the graph starts at -infinity and stops at the horizontal asymptote. So I'll end part A video here, and then I'll pick up with the rest of the note sheet on the next video.